Okay, hello everyone. In a new video, so we have reached part 10 of chapter 7, which is the Newton's second law for grade 11 students. Now in this one, what we are going to do is different, and we will introduce projectile motion, which is the title of section number 10. Okay, just 1 second. And let me write down the title of this section, which is given by projectile motion. So before I define what is meant by projectile motion, let me consider the following documents. So these documents represents events that happen in our daily life, and they are or reflect a physical situation or a physical phenomena. Not physical phenomena, but like a physical situation which is described as a projectile motion. So in the first document here, we can see a video game, which is the launching of this bird, and this game is known as the Angry Birds. So this game is based on a Newton's second law, and it's a particular case which is said to be a projectile motion. Okay, so all the scenes that happens in this game, in which we launch this with an initial speed and it hits a certain target later, this is known as a projectile motion. Also, if you consider this document where this boy launches the basketball with an initial velocity v to hit the basket, this is also known as a projectile. So also, if you consider this cannon, it's launching a shell with initial speed. So here the speed is indicated to be 600 feet per second. So this is also known as a projectile. So why it's important that we specify that these are projectile motions, because they will be governed by certain laws that we will discuss in this video or in this part, and all of these laws can be all of these equations can be determined by using Newton's second laws. I said that they are governed by certain laws, I mean certain equations, due to Newton's second law. So let me first state what is meant by projectile motion. Projectile motion is a motion of a body launched with an initial velocity and acted by the force of gravity which is the weight, in addition to a resistance but in most of the cases air resistance is neglected. So by air resistance I mean the force of friction due to air on the ball or on the bird or on this object. But in most of the cases the air resistance, which is considered as the friction force, is neglected. So we consider that there is no force of friction, okay? Otherwise the problem will be a bit complicated. Okay, so why all of these documents represent projectile? So why this bird, the motion of this bird will be projectile motion? Because simply it is launched with an initial velocity, and at any moment here the bird will be only subjected to force of gravity, which is vertically downward like this, which is the weight. So also why this ball it's considered, the motion of this ball is considered as a projectile motion, because along the trajectory, which is like this, the ball at a certain instant will be at this point, it will be only subjected to the weight and launch with initial velocity v. So why this cannon, the motion of this shell is considered to be a projectile motion? Because it's launched with initial velocity v0, say for example at any instant here along the trajectory. So it's being only acted by the weight which is vertically downward. The force, the air resistance, which is the friction force, may be somehow like this, so it is neglected. Okay, so we don't consider the force of friction. Now, what's the aim of this section? Is to determine the evolution of the system So here the system is considered to be the ball or the object, the evolution of the object with respect to time, simply the time equations. So in order to do so, let's consider a reference system given by xy. So suppose that this is the x-axis and this is the y-axis. And let's consider that this is the origin O. Anything along any vector lying along the x-axis can be described by the unit vector I, and any vector lying along the y-axis can be described by the unit vector J. Notice that this xy plane represents the real plane, okay? So this is the x-axis and this is the y-axis. And now here let's suppose that we have a certain object. So suppose here we have a ball initially at the origin O, and it's being launched with initial velocity v0. So initially the object S found at the origin O is being launched with an initial velocity v0, making an angle alpha with the horizontal. So v0 is the initial velocity, so taking t0 is equal to 0, and alpha is said to be the shooting angle. And let me here be specific that this is alpha 0. Okay, so now we expect, now as I said that the aim of this section is to determine the evolution of a system, so the trajectory of the ball, because now we are throwing the object like this or the ball, so the trajectory will be something like this. Let me do it properly. Okay, so what does this dotted line represent? This represents the trajectory of the object S, which is the actual path followed by S. This is the object S, which is lying here. Okay, so for example, one of the aims of this section is to determine the equation of this trajectory. Okay, now this can be done by studying the type of motion of the ball. So as you can notice that for all of these three figures, the trajectory, this is the trajectory. The trajectory here will be something like this, which will hit the basket, and this is the trajectory. So always the dotted line represents the trajectory of the solid S. Okay, so one of the aims is to determine the equation of the trajectory. Okay, now at any moment, so this is t0 is equal to 0. So this is time greater than 0. Now at a later time, if you consider S at a later time t, or let me say the following. At any instant t during the motion, whether t is equal to t0 or positive, S is subjected to its weight W vector. So this is the weight W acting vertically downward like this. So let's determine the projections of the weight. We have the Wx. Notice that if you consider this part, so this is the x-axis, this is the y-axis. Notice that these coordinate system can be moved and placed at any point that you are interested in. So in this case, the W vector has no projection along the x-axis, so Wx is 0. As for Wy is given by what? So this is the x-axis, this is the y-axis. It's completely lying along the y-axis, which is Wx is 0, and Wy in this case is given by minus W. So this is minus W. And now we are ready to apply Newton's second law, which is given by 2s, which is given by sum of forces is equal to ma, in which m represents the mass of the projectile. Now, what are the different forces that are acting on the projectile? We only have the weight, which is equal to ma. So now let's do the projection along the y-axis. So we have Wy is equal to may. So in this case, what does Wy represent? It's minus Wy, it's equal to may. Notice that we drop down the vector quantity, and each vector quantity will carry the label y. So W is given by m multiplied by g. G represents the value of the gravitational field strength which reflects on which planet we are performing this experiment. Though if we simplify by m, So this is simply given that ay is equal to minus g. So here we have an important result which is given by that ay is equal to minus g. Okay. So now what about the projection along the x-axis? So now let's drop down the vector quantity, and each vector quantity will carry the label x. We have that wx is equal to max. This is eventually 0, which is equal to max, which means that ax is equal to 0. So here we have a very important result. Now let's interpret this result. Okay. So here, let me adjust the figure to be aligned with the grids as much as possible. Okay. So here what do we have? We have that ax is equal to 0 and ay is equal to minus g. Okay. So now by using this, knowing that the acceleration vector is given by ax is equal to axi plus ayj, so we can decompose the motion along the x-axis and decompose the motion along the y-axis. Now let's start by studying So because we are interested in studying the type of motion, now we'll move to kinematics. Here on the scratch, let me write the different equations of motions that we use in UVM and URM and UVRM. So in the case of URM, we simply have x is equal to vt plus x0, v is equal to v is equal to a constant, and a is equal to 0. And in the case of UVRM, we have that x is equal to half at squared plus v0t plus x0, v is equal to at plus v0, and a is equal to a constant. Now let me say, since ax equal to 0 verifies the general equation which is given by a is equal to 0, then the type of motion is URM along the x-axis. So in this case, now we are allowed to use all of these equations. So we have that x is equal to vt plus x0, but notice that here we must distinguish between two components. So this is x, and vx is equal to a constant, and a is equal to 0. Now notice that vx is equal to constants, which means that the speed along the x-axis remains constant along all along the trajectory. So let me say along every single point of the trajectory. So this is important, only the speed along the x-axis, because the acceleration of the x-axis is 0, but the acceleration in total is not 0 because there is a variation in the y component. So if this is constant, what about it? Okay, so Vx is equal to constant, then it can be determined by referring to any instant of the trajectory, and in particular we can refer to the initial instant, which is given by t0. Okay, and in particular t is equal to t0. So in this case Vx is equal to V0x, which is equal to what? So notice that now we are determining the x component of V0. What does the x component represent? It's simply the projection of the V0 vector. Notice that here the V0 vector is simply given by V0xi plus V0yj. So in this case, if we are interested in determining the x component, which is the projection, so here it's pointing in the same direction of the x-axis, so it's plus, multiplied by the magnitude, which is V0, multiplied by the cosine of the angle between V0 and the x-axis, which is cosine alpha 0. Okay, so simply in this case V0x is V0 cosine theta 0. Similar to the fact that we get used to project, for example, the tension or the weight along an inclined plane. Okay, so because V is a vector component, it's equal to V0 because the speed is constant at all times, and here we are determining the projection along the x-axis, so it's simply given by V0 cosine. This is alpha 0 and not theta 0. Okay, so in this case these equations can be written as x is equal to V0 cosine alpha 0 multiplied by t plus x0. Now Vx, because it's constant, is equal to V0 cosine alpha 0, and Ax is equal to 0. And by this we are done with the first step, which is the type of motion along the x-axis. And let me here write the first set of equations that are given by, so we are done for example with URM. We will not use them in the y. Okay, so here we have that x is equal to V0 cosine alpha 0 t plus x0, and we have that Vx is equal to V0 cosine alpha 0 and Ax is equal to 0. Now we need to determine similar equations but for the y component. So now studying the motion along the y-axis. So now since Ay is equal to minus g, so minus g, what does g represent? The value of the gravitational field strength, verifies the general form. ay is equal to a constant, which means that we are talking about UVRM, then the type of motion is UVRM along the y-axis. So in this case, we can use the following equations that are given by y. So y is quadratic in time, which is given by half, and each quantity will carry the label y except for time. So Vy is equal to V0yt plus, Ay plus V0y, and Ay is equal to minus g, which is constant. Okay, so now directly we can replace these by minus g because we know their value, which is constant. Now what about V0y? So V0y is simply the y component of the initial vector V0. So if we refer back to the figure, and as usual, if this is alpha 0, then this angle is given by pi by 2 minus alpha 0. So notice that it's pointing in the same direction of the y-axis, so it's plus V0. Now here we have sine alpha 0. Why alpha carries the index 0? Because this is the initial angle alpha 0, because simply this is the name of the angle. Later on we will give alpha the angle between the velocity and the trajectory at any point. Okay, so now let's keep this to be alpha 0. So now we have determined everything. So in this case, we can rewrite these equations in the following form: y is equal to minus half g t square plus v0 sine alpha 0 multiplied by t plus y0. Vy is equal to minus gt plus v0 sine alpha 0, and ay is equal to minus g, and we are done. Okay, and let me write the equations of this projectile here. So we have that y is equal to minus half gt square plus v0 sine alpha 0 t plus y0. We have that vy is equal to minus gt plus v0 sine alpha 0, and ay is equal to minus g. Okay, so these are the time equations for a projectile motion submitted only okay. So these equations are the time equations of the projectile motion launched with an initial velocity v0, okay, and with a shooting angle alpha 0. Recall that the shooting angle is always this angle and not this angle. Okay, so whenever they specify this angle, this is the shooting angle. So now, for example, what if you are interested in determining the trajectory? the actual path followed by the projectile. And recall that the trajectory is the relation between x and y. So now here we have that x is equal to v0 cosine alpha t plus x0. And we have that y is equal to minus half gt square plus v0 sine alpha 0 t plus y0. Now, in order to determine that trajectory, we need a relation in terms of x and y. So now we need to extract t from one variable and replace it in the other. So now we refer to the linear variable which is given by x. And now let's consider the particular case in which x0 is equal to 0 and y0 is equal to 0. And this is the case because we are launching s from the origin. In other exercises, it may happen that we may launch the object as from here. So x0 in this case will be 0, but y0 will be different than 0, okay? But now let's consider the simple case in which x0 is 0 and y0 is 0. x0 is equal to 0 and y0 is equal to 0, launched from the origin. So now if you extract time from here, time will be given by x divided by v0 cosine alpha 0. Replace t in y, we have that y, sorry, replace t in y, yes. So I'll have y is equal to minus half g x divided by v0 cosine alpha 0 to the power 2 plus v0 sine alpha 0 multiplied by t, which is x, v0 cosine alpha 0. Now v0 got out with v0, sine alpha 0 over cosine alpha 0, this will give us tangent alpha 0. So this over this is given by tangent alpha 0. So here we have that y is equal to minus half g x square divided by v0 square cosine square alpha 0 plus tangent alpha 0 multiplied by x. So now y is equal to minus half g 1 over, or let me write it this way, minus g over 2 v0 square cosine square alpha 0 multiplied by x square. So all of this is a constant we can determine, plus tangent alpha 0 multiplied by x. Okay, now if y0 is different than 0, here we will have another term which is y0. Okay, so now what's the type of this trajectory? This is a parabola. Why? Because simply it's quadratic in one variable and linear in the other. And indeed, if you refer to the trajectory followed by the projectile, notice that I have traced this as if it was a parabola. So this is the trajectory, which is a parabola. Okay. Now also let me introduce the range. So what is the range? Let me define the range. Range is the horizontal distance covered by the projectile between the shooting point and the point of intersection with the horizontal line passing through the shooting point. So let me explain what's the range. The range is the horizontal distance from the shooting point. This is the shooting point, okay, to the point of intersection of the ball or the projectile with the horizontal line passing through the shooting point. So simply this is the range. The range is the distance from here to here. Let me repeat the definition. So here, range is the horizontal distance covered the projectile between the shooting point and the point of the intersection with the horizontal line passing through the shooting point. So this is the shooting point, and this is the point of intersection because this is the horizontal line. So this is the range. Now we are interested in calculating the range. Okay, so the range must be expressed in meters. So how do you determine the range? So using the trajectory equation, now we have that y is equal to minus g divided by 2v0 square cosine square alpha 0 x square plus tangent alpha 0 x. So now we set y is equal to 0. The range corresponds to y is equal to y0 is equal to 0. So in this case, the range corresponds to the equation which is given by y is equal to y0y, because the intersection point must be at the same horizontal level of the shooting point, and this is given by y is equal to y0. So the range is given by the equation y is equal to y0, okay? This is the range. In which this equation in which we determine the range. In this case, because y0 is equal to 0, so y is also equal to 0. We have that 0 is equal to minus g divided by 2v0 cosine square alpha 0. Now x in this case represent the range, so x square plus tangent alpha 0 multiplied by x. Now we are interested in finding the value of x, which represents the range. So what's the type of this equation? This is a quadratic equation in x. So how do we solve it? We have two methods. Either we go and calculate delta, or we solve by factorization. So let's solve by factorization. We take x as a common factor. We have minus g divided by 2v0 square cosine square alpha 0 x plus tangent alpha 0 equal to 0. Since x is different than 0, then we have that minus g divided by 2v0 square cosine square alpha 0 x plus tangent alpha 0 is equal to 0, which means that x is given by, if we rearrange the equations, it's given by 2v0 square. Let me say, okay, let me do it explicitly. So minus g divided by 2v0 square cosine square alpha 0, which is equal to minus tangent alpha 0, this goes out with this, then x is given by 2v0 square cosine square alpha 0, tangent alpha 0 can be written as sine alpha 0 divided by cosine alpha 0, this goes out with this, divided by g, so we are left with 2v0 square cosine alpha 0 sine alpha 0 divided by g. Okay, so now let me replace x by r. So I repeat, what is the range? The range is the distance when y is equal to y0, because y, when the intersection point is in the same horizontal level with the shooting point, okay? So now x must be replaced by r in order to reflect that this is the range. So I repeat, the range is the horizontal distance separating the shooting point with the intersection point of the trajectory and the horizontal line. So actually it represents this distance in meter. So r is given by, now notice that here in this case we have 2 cosine alpha 0 and sine alpha 0, and we know that 2 cosine alpha 0 sine alpha 0 can be written as sine 2 of alpha 0. So r v0 square sine 2 alpha 0 divided by g. Okay, so this is the range. Now how do we obtain maximum range? So r is maximum when, so notice that here sine of this angle, which is 2 alpha, sine 2 alpha 0 can ranges from, say for example, greater than 0 and less or equal to 1. So it's maximum when the sine alpha 0 is equal to 1 because it's the largest value, which means that 2 alpha 0 must be equal to pi by 2, which means that alpha 0 is equal to pi divided by 4. So let me write the following remark. Whenever we want to launch a projectile and to reach the maximum horizontal distance corresponding for the range, then the shooting angle must be alpha 0 is equal to pi by 4. Why? Because this quantity is a variable quantity. Now considering that v0 and g are constant and we want to maximize this quantity, so we take it's equal to 1, which means that 2 alpha 0 must be pi by 2, which means that alpha 0 must be pi divided by 4. Now the last idea I want to discuss for this video is the maximum height. Okay, so the maximum height so at any instant t or at any instant along the trajectory, the height or the vertical distance is defined by the distance from the horizontal level to the peak. So the maximum height is given by Vy is equal to 0. Why Vy is given to 0? So here if you consider this trajectory, the maximum height will be somewhere here. Okay, so the maximum height will be somewhere here. This is the maximum height reached by the projectile. Okay, so this point corresponds for the maximum height, and we are interested in determining this height h. Okay, now if you consider the velocity vector at this instant, the velocity vector is always tangent to the trajectory, so this is the velocity vector v. So notice that in this case, what are the projections of v at the maximum height? Vx is given by, okay, we have Vx, but what about Vy? It's completely lying along the x-axis, so Vy is equal to 0, okay? For this reason, at the maximum height, the velocity vector is tangent to the trajectory. Always the velocity vector is tangent to the trajectory. So because it's a parabola, at the maximum height, Vy will be given by 0, okay? So now if we drag the expression of Vy, which is given by minus gt, so Vy is equal to minus gt plus v0 sine alpha 0. We are interested in determining the instant t. So setting Vy to be 0. Why Vy must be 0? Because at the point where the projectile reaches the maximum height, if we consider the velocity vector like this, it has no y component, so simply Vy is given by 0. So in this case, t is given by okay. But now if you are interested in determining this height, which is corresponding for capital H, we know that y is given by this expression. So y, which is equal to minus half gt square plus v0 sine alpha 0 t plus y0, replace in y. So this will be capital H for the maximum height. Y is replaced by capital H, which is minus half g into v0 sine alpha 0 divided by g to the power 2 plus v0 sine alpha 0 multiplied by v0 sine alpha 0 divided by g, and suppose this is given by 0. So capital H is given by minus half. Now here this g because to the okay, let me do them explicitly. So this goes out with this because this part is for also for g, so it's given by minus half v0 square sine square alpha, okay, g. So notice that here we are adding two quantities, two same expressions, but here minus half with plus 1, so this will be given by v0 square sine square alpha 0 divided by 2g. Okay, because this is minus half and this is plus 1, so minus half and plus 1, which is equal to half. So in this case, the maximum height is given by v0 sine square alpha 0 divided by 2g. So these are all the quantities that we are interested in for the projectile motion. But there is also an additional thing, which is the direction of the velocity vector, which is tangent to the trajectory. I will leave it for other parts and we will solve exercises on the projectile motion. Okay, so that's it for me in this video, guys. In part 11, we'll complete the explanation and solve some exercises.